Good morning to everyone. Welcome to today's webcast, Vallourec High Strength Grades for Complex HPHT Wells. I'm Jonathan Oliveira, Marketing and Development Coordinator of OCTG Grades at Vallourec, and I will be your moderator today. In this webcast, we will discover how Vallourec proprietary high collapse and high strength grades can help you optimize your well design with lighter strings, all while maintaining your safety margins and reducing cost. I am with Maria Beatriz Ibarra, Vallourec Marketing and Development Manager, and during this webcast, she will provide you concrete examples of how your high collapse and high strength grades can help you overcome oil and gas industry challenges at a competitive cost. Following the presentation, we will have a short question and answer section. You can participate in the Q&A section during the presentation by typing your question into the Q&A chat. Now, let's get started.
Thank you, Jonathan. It's very nice to be here, and I would like to welcome all participants to this webcast on high-strength grades for complex, high-pressure, high-temperature wells. I am glad to see the high level of interest on the topic, and I hope that you all learn something new during this exchange. This webcast will cover the following topics. I will do an introduction of Vallourec and a brief overview of our presence in oil and gas industry, supplying pipes and integrated solutions for downhole applications. Then, I will briefly introduce the main challenges in oil and gas industry where enhanced collapse and burst resistance are required, focusing mainly on high-pressure, high-temperature wells. Following, I will give an insight of how the mechanical performance and sour service resistance of a steel are linked, and discuss how both properties are guaranteed in our line of high-strength sour service material. This session will be completed by an actual case study with very high mechanical requirements in a severe sour environment in Gulf of Mexico. Then, I will give an insight in our high collapse proprietary methodology, explaining why we are able to achieve enhanced performances while remaining the safest choice in the industry. And we will focus on a case study where a very high external pressure resistance was required on a very challenging high pressure, high temperature well in Gulf of Mexico. Following, we will focus on how the internal pressure resistance of a tubular can be enhanced, and discuss a case study where enhanced burst resistance was mandatory for a complex wasted well design in Southeast Asia. Then, I will give an overview of our high-strength portfolio and finalize my presentation with some conclusions before opening our questions and answers section. Vallourec is a worldwide company with several decades of experience supplying OCTG pipe solutions around the world. We have built a strategic industrial footprint close to our customers to address their needs more locally and deliver faster your casing pipes. Our expertise in material development, well design, and material selection related to OCTG applications, combined with our expertise in pipe processing, are available to support you in your projects. Let's start with a quick review of the main internal and external pressure challenges encountered by drilling operators. For many years, oil and gas operators have faced increasingly high mechanical loads during drilling and production operations, such is the case of high pressure, high temperature or HPHT wells. The addition of these high mechanical requirements and the high temperature levels that lead to a mechanical derating of the tubulars have led to heavier and more complex well designs that can withstand such demands. In addition to this, sometimes these loads are accompanied by sour environments, adding an extra layer of complexity. In this webcast, we will be focusing on the mechanical loads related to the internal and external pressure. When the external pressure exerted on a string is higher than the internal pressure, we are in the typical case of a collapse load. The main and most challenging collapse loads that are encountered during drilling phase are the cementing operations and the full evacuation loads. On the first case, the external pressure given by the column of the cement slurry outside of the casing is much higher than the internal pressure exerted by the displacement fluid on the inside. This creates a collapse load that increases from the top of cement towards the bottom hole. The second case, the full evacuation load case, is considered to be one of the most critical collapse loads, and it represents the complete displacement of the drilling mud out of the wellbore. This means that no hydrostatic column is left inside of the casing, so there is no internal pressure to counteract the external pressure applied by the formation, leading to very challenging collapse loads. The third important load to be considered is the annular pressure buildup, or APB, caused by thermal expansion. During production operations, the temperature of the string increases, leading to an expansion of the confined fluid in the annular space and creating both an external pressure on the inner casing string and an internal pressure on the outer casing string. These loads become more critical on deep water wells, where mitigation methods become more limited. In addition to this, operators are often faced with the opposite situation, internal pressure being higher than the external pressure, commonly called burst loads. These are very critical mechanical loads, since a failure of the tubular can lead to a loss of the well control. The most critical burst loads during drilling operations are the high pressure test and gas kick load cases. The high pressure test refers to a high pressure applied in the wellhead in order to simulate the highest internal pressure expected during the well life, commonly linked to the fracking operation. The second case, the gas kick, simulates a bubble of gas entering the string and replacing part of the drilling mud, exerting an internal pressure on the string equal to the formation pressure and leading to very challenging burst loads. During production phase, the most critical burst loads are linked to the annular pressure buildup, as explained previously, and the tubing leak. In this case, it is considered that the production casing is in contact with the formation fluid and suffers an internal pressure that is equivalent to the formation pressure. We have seen that with the evolution of drilling operations drifting towards offshore and deep water and HPHT wells, mechanical loads become more and more severe. As a consequence, API grades are no longer able to cover all the requirements, and dedicated proprietary grades become a must. For this kind of application, Vallourec offers the high collapse and high burst grades up to 150 psi of a specified minimum yield strength. For environments with H2S, we can find these grades in combination with sour service resistance up to 130 psi of specified minimum yield strength. Let's see these grades in detail and how they can add value to your operation. Let's start by discussing how the mechanical and corrosion resistance of a tubular interact with each other. And the first question I would like to address is, what happens when we are in a sour environment, and why is it so critical for the safety of the operation? When we are in presence of H2S or hydrogen sulfide in combination with water, these chemicals react and release free hydrogen, decreasing the environment's pH. Due to the small size of this molecule, the free hydrogen can penetrate the material, occupying interstitial spaces, that is, spaces that are normally free between the iron and carbon atoms. Hydrogen embrittlement occurs most significantly, but not exclusively, at local stress locations, which then leads to cracking due to the combination of stress and embrittlement. And so, the material is susceptible of suffering a failure even below its specified minimum yield strength. This phenomenon is called sulfide stress cracking, or SSC, and can happen even at very low concentrations of H2S. For this reason, the international standard NACE-MR 0175 recommends using sour service grades for partial pressures of H2S that are higher than 0.05 psi or 0.003 bar. Now, how does this impact the well design? When operators are faced with challenging mechanical loads in the well, the natural first answer is to increase the mechanical resistance by increasing the specified minimum yield strength. However, when in presence of H2S, this is not always possible, since by increasing the mechanical resistance, the material toughness and ductility are reduced, making the material more susceptible to the phenomenon of hydrogen embrittlement, and as a consequence, more susceptible of failure due to sulfide stress cracking. For this reason, dedicated sour service materials are required for such applications. Depending on the severity of the sour environment, Vallourec offers a wide variety of sour service resistant materials in combination with high mechanical properties. For mild environments, generally regions 1 and 2 according to NACE-MR 0175, we are able to offer mild sour and severe sour grades with specified minimum yield strength up to 130 psi. For more severe environments, generally regions 3 and 4, we offer extreme sour and enhanced severe sour grades with specified minimum yield strength up to 125 psi. All these grades are also available in combination with high collapse and extreme collapse resistance. Now, let's see how, in some real case examples, these grades can support you on your operations, where high mechanical resistance is required in combination with sour service resistance. For the case study number 1, we have prepared an offshore high-pressure, high-temperature case from a customer in Gulf of Mexico. In this case, the project was the typical nested well design from this kind of operation, meaning that the mechanical resistance of the tubular could not be increased by simply increasing the wall thickness of the pipe due to very tight tolerances between the strings. On the other hand, the highest sour service grade was not enough to meet the external and internal pressure loads, and a dedicated grade combining both high collapse and sour service resistance was needed. As a solution, we were able to offer a grade that combines these performances, acting as a project enabler. Let's see the customer request in details. From a mechanical point of view, the minimum required burst resistance was 16,200 psi, and the collapse resistance was 1,170 psi. In addition to this, a resistance to a mild sour environment with a pH of 4.5 and a partial pressure of H2S of 0.2 psi was requested. The customer original well design included the VM125SS, a sour service grade with a specified minimum yield strength of 125 psi that has been qualified for this region 2 condition. However, this product could not meet the mechanical requirements being well below of both the internal and external pressure needs. As mentioned before, the only alternative seemed to be to increase the wall thickness, but this was not possible due to the very tight tolerances for the OD and the drift. As a solution, we were able to offer the VM130 HCMS, a mild sour grade with 130 KSI in combination with high collapse properties. This product not only allowed to keep the original design, but also to increase their safety margins, all while covering the corrosion resistance needed by the customer. For this case, we launched 3 fit-for-purpose NACE A corrosion tests in our laboratories in France, simulating the operation conditions. All NACE A tests passed, showing no crack and no rupture, proving that the grade was suitable for this condition. Now, let's focus on the external pressure resistance of a tubular, and let's discuss how it can be enhanced thanks to our proprietary methodology. For many years, Vallourec has worked on developing and continuously improving a proprietary high collapse methodology to deliver the highest and safest performance in the market, bringing solutions to our customers in all types of applications, from the most standard conventional application to the most critical deep water projects. Our methodology is supported by 3 stages of design and manufacturing process. The first step is the product design. During our decades of experience, we have identified 5 manufacturing variables that drive the collapse performance of a product. These variables are related to the pipe's geometry, such as the wall thickness, ovality, and eccentricity, as well as to its mechanical performance, such as the residual stress and the yield strength. Based on our proprietary high collapse model input and our experience, the target values for these variables are set during the product design process and then controlled during production in order to guarantee that the targets are met. Generally speaking, the tighter and more controlled these parameters are, the higher the collapse rating of the production will be. Then, quality control is performed applying the individual pipe analysis. Each and every high collapse pipe is inspected with an automated system to 100% of surface coverage with high resolution for both external diameter and wall thickness. A much more complete inspection than API requirements. In a word, this proprietary quality control procedure guarantees that every single pipe from the production lot is inspected and verified to achieve the targets set during the product design. In addition to this, regular random physical collapse tests are run according to Annex I of API 5C3 requirements in order to give continuous feedback on our model. All these steps allow Vallourec to offer the highest and safest collapse ratings in the market. We have seen more recently operators asking for higher and higher external pressure resistance, many times above what standard high collapse products could offer. As an answer to this, Vallourec has developed the Extreme Collapse offer, a premium alternative for heavy and complex well designs. Our Extreme Collapse offer includes the single basket and the dual performance basket alternatives. Let's start with the single basket alternative. We have said before that in order to obtain the high collapse performance, we need to apply stricter manufacturing rules than those used for API grades. So, what happens when we push the manufacturing rules even beyond those used for HC grades? To answer this, let's focus on the graph on the upper left side. On the horizontal axis, we can see any manufacturing parameter that has an impact on the collapse resistance of a product, the ovality, the eccentricity, the wall thickness, etc. On gray, we can see the normal distribution of an API product. As the manufacturing parameters are not tightly controlled, the distribution is scattered and the final collapse rating is quite limited. We see that when the control of such parameters is tighter, the scattering is more controlled and the final collapse rating is higher. That is how high collapse resistance is obtained. On this case, it is represented in light blue on this graph. If we set even tighter manufacturing rules, we increase the collapse rating even more, and we obtain the extreme collapse grades. In this case, they are represented on pink. As we can see on the graph below, on this offer, 100% of the order is now delivered with this higher extreme collapse rating. Now, let's evaluate the second alternative. The dual performance basket methodology that consists on identifying and segregating the most performing pipes of a production lot by means of accurate dimensional pipe data and individual pipe performance prediction. Like this, the most performing pipes are identified and physically sorted into the premium basket with a higher extreme collapse rating. This basket is then placed by the operator into the most demanding sections of the well. The remaining pipes are part of the regular basket and assigned the standard high collapse rating, and then placed by the operator on less critical well sections. Additionally, and for logistics simplicity, each basket has its own marking and mill certificate. As we can see on the graph at the lower right side of the slide, this alternative allows to increase the collapse rating of 50% of the order at a marginal cost. In summary, the extreme collapse offer can represent a project enabler for cases where the collapse loads are beyond standard and high collapse grades cannot meet the needed requirements, or even to make the operation safer by increasing the safety margins. In addition to this, it can also allow operators to switch to a lighter weight, thus leading to a simpler operation by increasing the clearance of the string. Now, let's see this new offer applied to a real case study. In this case, we will again be focusing on a sour service offshore HPHT well in Gulf of Mexico, where the challenge will be combining higher than standard collapse rating with a sour environment for the intermediate casing. Once again, due to very tight tolerances between the strings, it is not possible to increase the mechanical resistance of the tubular by simply increasing its wall thickness. The solution offered by Vallourec was a dual performance basket in VM125 HCSS grade that allowed to an increase of 8% in the collapse rating while still maintaining the original well design. Let's focus first on the operator needs. A tubular combining a severe sour resistance with a minimum collapse resistance of 5,850 psi. It is important to mention that, in this case, the external pressure increased with the depth, and this elevated collapse resistance was needed only on the bottom half of the string. Let's have a look now at the different alternatives this customer was looking at. The original design was a 16.15 inches, 119 pounds per feet of weight, and a drift of 14.6 inches on the highest available grade combining both severe sour resistance and high collapse performance, a VM125 HCSS. However, we see this alternative offers a collapse rating of 5,650 psi, well below the minimum requested of 5,850. This resistance could be enhanced by increasing the wall thickness. We see that by moving to a 127 pounds per feet, the collapse resistance is increased to an acceptable value of 6,940 psi. However, this alternative is not acceptable by the operator since the drift was reduced to a value that could severely complexify the drilling of the next section. The only alternative left was to move to a higher non-sour grade. We see that by keeping the original weight of 118 pounds per feet and switching to a VM140 CYHC grade, we are able to achieve a collapse rating higher than the minimum requested. However, this grade does not offer sour service resistance, and the risk of having a failure due to sulfide stress cracking is considerable. So, in one word, there was no solution at the time for these customer challenges. Since the elevated collapse loads were found only on the bottom half of the string, having the 50% of the string with a higher collapse rating was enough for this project, and the dual performance basket on a VM125 HCSS became the solution to offer both the mechanical and corrosion resistance for the customer. As a reminder, this methodology consists on identifying and segregating the 50% most performing pipes of a standard high collapse production into what we call the extreme basket. That was then placed by the customer where the collapse rating were expected to be the highest. The remaining 50% of the order was segregated into the regular basket with the standard HC rating, and then placed by the operator in the less demanding sections of the string. This means that the rejection rates remain at very low values, and this extreme collapse performance is achieved at a marginal cost related mostly to the logistics of segregation. Now, let's analyze how the internal pressure or burst resistance can be enhanced on a tubular. According to the MIYP model, burst resistance is mainly driven by two parameters: the wall thickness and the yield strength of the tubular. This means that one way to boost the internal pressure resistance is by increasing the remaining body wall, or RBW, of the pipe. The international standard API 5CT requests a minimum of 87.5% of remaining body wall but increasing, let's say, to 92.5% of remaining body wall, the burst resistance can be greatly increased. The second alternative to boost the burst resistance is to increase the specified minimum yield strength of the grade. However, API products can only offer a limited yield strength, being Q125 the grade with the highest specified minimum yield strength according to API 5CT. In order to offer an alternative, Vallourec has developed 4 dedicated grades with higher yield strength levels called CY, or controlled yield grades. 3 of them, VM125CY, VM130CY, and VM140CY, are 100% compliant with API Q125, meaning that they cover all the requirements plus having more restricted values of yield strength in order to offer an enhanced burst resistance. However, for some challenging projects, this was just not enough. which is why we have developed the BM150CY with the SMIS of 150 KSI, the highest in the market. In one word, today we are able to offer a solution to your most challenging birth requirements thanks to a combination of higher than API specified minimum yield strength and remaining body wall. Let's move on to the last case study of this webcast that analyzes how these CY high strength grades can add value to your operations. We will now analyze an offshore deepwater HPHT well located in Southeast Asia. In this case, the operator was facing very high internal pressure levels due to the pressure tests related to the fracking pressures. In addition to this, tolerances were very limited, meaning that the customer could not increase the well thickness without impacting the whole well design. The solution proposed by Vallourec allowed the customer to meet the mechanical requirements and keep the original well design. Let's see how this was done. To summarize the customer requirements, a maximum OD of 9 5/8 and a minimum drift of 8.5 inches were mandatory while achieving a minimum burst resistance of 14,300 psi. The customer first choice was a Q125 grade with a minimum remaining body wall required by API of 87.5%. But the burst resistance was 12,390 psi, well below the minimum requirement. Even by increasing the remaining body wall up to 92.5%, the internal pressure resistance was not enough, leaving the operator only with the alternative to move to a thicker tubular and reducing the drift, which was not acceptable by the operator. In one word, the API grades were not able to offer a solution. Thanks to a combination of our BM140CY grade and a remaining body wall of 92.5%, we were able to offer a minimum guaranteed burst resistance of 14,670 psi, an alternative that allowed the operator to keep the original well design while maintaining the needed safety margins. During this webcast, we have mentioned several different grades with different combining mechanical and corrosion performances. And I would like to finish my presentation by summarizing our high strength offer. API grades offer a limited collapse and burst resistance that, as we have seen during this presentation, is often not enough for several applications, and particularly for high pressure, high temperature wells. As we can see on the vertical axis, the internal pressure or burst resistance can be increased by moving to higher grades, such is the case of high strength sour service grades, such as the BM125SS or BM130MS. It can also be increased by switching to a dedicated high-strength grade, such as is the CY family ranging between 125 and 150 KSI of specified minimum yield strength. On the horizontal axis, we can see that the collapse resistance of a tubular can be increased by moving to high collapse grades that offer an enhanced external pressure resistance thanks to a more restrictive manufacturing process than used for API grades. When an even higher collapse resistance is needed, then we can move to extreme collapse grades that can be achieved by either restricting the manufacturing rules even more than for standard high collapse grades, or by the dual performance basket methodology that identifies and segregates the most performing pipes of the lot. Now, both higher burst and collapse resistance can be combined between each other on the CYHC and CYXC grades, or together with sour service resistance on the HCSS or XCSS grades. Our high-strength offer covers the OD range from 4.5 to 26 inches, including non-standard sizes, and all products are qualified with our proprietary VAM connections. But how do we qualify our VAM connections? All our VAM products are validated following the latest and most severe testing standards, such as API RP 5C5 2017 and ISO 13679 2019, as well as the most rigorous R&D criteria. This involves a very detailed performance demonstration and extensive testing on critical configurations in terms of geometry, size, grade, torque, temperature, and others. This includes as well physically testing the connection to the highest actual collapse rating, a point that is particularly critical for high collapse and extreme collapse products, and leading to a comprehensive validation for the most severe requirements. Some examples of our severe qualification procedure are the qualification of VAM 21 with VM 125 and 110 high collapse sour service grades for critical onshore salt dome applications in South America, and the qualification of VAM SLIG 3 with VM 140 high collapse and high strength grades and 130 high strength for a challenging high pressure, high temperature and deep water wells in Gulf of Mexico. So, in order to guarantee that you have access to the safest and most reliable product, make sure you request the connection qualification test reports to your high collapse supplier. Well design optimization is a complex challenge with so many important parameters that need to be taken into account. As Vallourec, we have a multidisciplinary team of experts to help you make the right choice from our wide portfolio of material and connections. We are here to help you from the design phase of your project through to fit-for-purpose testing and controlling every step of the process to ensure that you optimize the well design and enhance well integrity. This is the value of our service, and this is where we can deliver really cost-effective solutions. Thank you for listening. I am now ready to take your questions.
Thank you, Beatriz. We will now transition to the questions and answer portion of our webcast. You can continue to submit your questions in the Q&A chart. So let's start with our first question. So, is the single basket offer guarantees a higher collapse rating for 100% of the order? Why would the dual performance offer that guarantees it only the 50% of the order be attractive for the operator?
Okay, so I understand then that the question is why, if the dual performance basket guarantees an extreme collapse rating only for 50% of the order versus the single basket that guarantees for 100% of the order, why would someone choose the dual performance basket? I understand that is the question. So let me go back to the previous slide. I think it can help me answer the question. This is the slide I was looking for. So it's actually a very good question. So what we were saying before is that in order to obtain, let's start from the basics, let's start from API products. And we have said that in order to obtain high collapse products, we need to target tighter manufacturing rules, and then we get the high collapse products. Of course, the fact that we are moving from the API manufacturing rules to tighter, more control, more demanding, more challenging for the mill manufacturing rules, this is going to bring a cost. And this cost is related mostly to rejection rates. The more demanding the manufacturing rules are or the targets are, the higher the rejection rates are going to be at the end of the day. So if we target even tighter manufacturing rules in order to achieve this extreme collapse single basket solution, then the rejection rates are going to be higher than the standard HC grades, which means that the cost, the final cost, and that are related mostly, but not only, to the rejection rates are going to be higher. So to put it very simple, the extreme collapse single basket is going to be more expensive than the standard high collapse product. That is on one side. Now, let's focus then on the dual performance basket. What we do for the dual performance basket is we produce a normal HC or high collapse order following the standard high collapse manufacturing rules, okay? And what we do is from that order, we do an individual pipe analysis, and we say, okay, from this order, these are the 50% most performing pipes, and we physically segregate them and put them aside. So at the end of the day, you will receive on your yard two different, what we call baskets, so two different groups of pipe that are segregated according to the mechanical properties, to the collapse rating resistance, to put it very simple. So what I'm saying is that the costs related to the rejection rates are going to be the same as for the standard high collapse product. However, the dual performance basket is going to be slightly more expensive than the standard high collapse because we have this extra step at the mill of identifying and segregating the most performing pipes. So it's going to be slightly higher, but it will still remain at a lower cost than the single basket offer. So both options, they have the advantage, we can say, of offering this higher extreme collapse rating. One is cheaper than the other, and one offers 50% of the order with this higher collapse rating than the other.
Okay, I have another question, Beatrice, that is still on the XC and the HC performance. So, okay. So I will say it. When you reference manufacturing controls, do you mean inspections acceptance controls? The chart suggests you determine XC and HC performance by inspection, not by specifically changing the production controls. I expected you would have better than a 50-50 mixed if targeted production controls are applied. If you want, we can cut because we have several questions on this one. You can take one by one. So if we start by the first one, when you reference manufacturing control, do you mean inspection, acceptance controls?
Okay, so there are two things. Yes, our high collapse and extreme collapse offer, they have an inspection or quality control process that is tighter than the standard API product, right? So at the end of the day, that is one of the strengths of our high collapse methodology, and it's one of the steps that will allow us to offer this to offer these higher performances. So just to put it very simple, what we do for our high collapse and extreme collapse offer is that we check pipe per pipe in order to guarantee that the targets, the production targets that were set are achieved. So at the end of the day, you know that every single pipe that you receive from a high collapse or extreme collapse or lot or order will achieve the collapse rating that we have guaranteed to you. That is on one side. And maybe I'm just gonna put this slide. So I was just now discussing about this step 3. However, there is also the production control. So yes, we control tighter than for API, but we produce tighter than for standard API. So for example, what I mean is that for the wall thickness and the yield strength, for example, that these are parameters that are set in API 5CT for different products, we control even tighter than that, which means that the wall thickness, we're going to control it tighter in order to push it to the upper limit of the range accepted by API, and so is the yield strength. So we are still compliant with API, but we are tighter, pushing the limits even tighter in order to we can say to obtain this higher collapse rating, okay? And that is also the case for eccentricity, ovality, and residual stress, that they are not controlled in API products, but for high collapse products, we control it. It's part of our process. So we do not only control in the quality control or the inspection section, but we also, during production, we need to target more restricted and more challenging manufacturing rules or processes, as you would like to call it, in order to actually achieve higher collapse ratings.
Okay, and then the second question, which are in this big question, is the chart suggests you determine XC and HC performance by inspection, not by specifically changing the production controls. I think here the question is related to the way we can do extreme collapse by getting tighter the manufacturing parameters, but also getting extreme collapse by dual performance basket, right?
Yes, it is exactly that. It's a very good point, because this is exactly how we obtain the high collapse and the extreme collapse, not only by controlling better, but also to producing better, we can say. And then I see that the last line, I expect you would have better than a 50% 50 mix if targeted production controls were applied. And that is completely true. And that is the difference between the single basket and the dual performance basket option.
Okay, thank you. So now I will try to take a question on the control yield grades. So we have several ones. I will start it by this one. So when you talked about burst, are you referring to the pressure value at the onset of yield at the internal fiber, or of the pipe, or the actual rupture value? These numbers are not the same.
Yes, you're right. Those numbers are not the same. So to be very a little more specific, when I'm talking about this, I'm referring to the Barlow MIYP equation and not to the actual burst pressure.
Okay, thank you. I would take another one, also still on the control yield grades. Let's see. Are you changing the metallurgy of these control yield grades, or it is simply effect of tighter tolerance during manufacturing?
So I would say it's both. because on one side, our VM 125 and 30 and 140 CY and they are fully compliant with Q125. What this means is that we follow the chemistry that is set for Q125 according to API 5CT, but we have a proprietary chemistry that is more restricted than what API 5CT requires. So the most detrimental elements are reduced even more, so the limits are set at a lower value, and the elements that are going to help us increase the mechanical properties and so on, they are increased to the higher limit of the range set by API 5CT. So that is related to the chemistry. So fully compliant with Q125, but more controlled chemistry than standard Q125. And then, as you mentioned on your question as well, yes, also the production process is more controlled than for standard Q125, because we do not only need to target a higher SMYS for the case of the 130 and 140 and 150 KSI, but also the yield strength range is very limited. And it's very challenging for the mill to produce. It's only 10 KSI between the minimum SMA yield strength and the maximum allowed yield strength. So it's very challenging to control like this, and we do both things, chemistry and production control.
Okay, we have another question still on the control yield. I think it's referring to the 150 CY, our VM 150 CY. So the question is, at 150 to 160 KSI, how do we ensure consistency of through-wall hardness and ductility with a shear area higher than 60%?
Okay, okay, perfect. So here I think, yes, we're talking about the VM150 VM150 CY that goes from 150 to 160 KSI. I think that's the grade that we are talking about here. Yes. So there are three things that we do, to put it very simple, in order to control the variation of the harness through the wall. So one thing is the lean chemistry that we were talking about. It's the compliant with Q125, but more restricted, more control, and richer on the elements that are good for the mechanical properties. That is on one side. Then we do have stricter values than Q125 for the maximum harness value, but also the maximum variation that we accept for the HRC values. And then the third, the third item that we control is also we perform for quality control. We perform Sharpie tests that need to show a shear area that is at least 75%. So those are the three things we control: the chemistry, the harness values and variation, and the Sharpie.
Okay, thank you. Another quick one for control yield grades. So do CY grades offer sour surface resistance?
Okay, so here maybe I would like to do two parts answer. So normally speaking, when we talk about the sour resistance of a material, we talk about low temperature. So either 24 degrees or room temperature, but it can also be 4 degrees, which is the seabed temperature. So normally, in order to confirm the corrosion resistance or surface stress cracking resistance of a material, NACE A tests are performed at these low temperatures. Why is that? And this is, I'm just gonna go back to the previous slide. This is related to the discussion we had on this slide because we said that when the material becomes more brittle, then the risk of cracking due to the presence of H2S becomes more risky, becomes greater. So another thing that we need to consider is that the material also becomes more brittle at low temperature. So normally when we talk about the sour service resistance of a material is because we perform the NACE test at the lowest temperature the material is expected to see, either room temperature or seabed temperature. So the CY grades, high strength grades, they are not supposed to be used at such low temperatures. They do not have sour service resistance at 4 degrees or 24 degrees. However, the fact that the yield strength is more restricted, so for example, the VM125CY goes from 125 to 140 KSI, the fact that we cut it at 140 and not at 150 KSI, it means that the risk of the material losing the toughness due to this very high yield strength is more controlled. So CY grades can be used in some sour environments at high temperature levels. So not at 24 or 4 degrees, but at high temperature levels from the top of my mind at 80 degrees or something like that, depending on the grade. Then the 150, I think, is started at 107 degrees, I think. So they can be used in sour environments, mild sour environments at high temperature levels. If you have a particular project that you would like to use CY grades and you have sour environments and you would like to know if it's feasible or not, please contact me. My email is on the last slide, and we can share with you the corrosion test results that we have and guide you whether the CY grades could be used or not and what could be used instead if this is not the case.
Okay, so now switching a little bit to high collapse again. Are collapse tests performed to failure or an additional external pressure test to the rating or pressure above the rating?
So the question is if we perform physical collapse test up to failure or not. Okay, perfect. So it is very important to perform the test up to failure in the case of collapse grades because it's internally it's important for us also in order to give a feedback to our proprietary model, to know adjust or to give a continuous feedback and adjust the model with time. So it's important, and we do it as a standard rule in all our mills, in all our Vallourec mills. Then there are some products where we have products that are very commonly sold. So we have a very vast database of collapse tests. Then in those cases, we can discuss with the operator to see if we could perform a waiver on the testing of on this kind of product. And it's always with the okay and the agreement from the operator.
Okay, we have two more questions, so let's just see. I will take a quick one because we are very short in time. I have a project where proprietary high collapse or high strength grades could help us optimizing the well design. Where can I get the collapse ratings for your products to run my simulations?
Okay, so the answer I'm gonna give is not only valid for for collapse resistance, but it's also valid for internal pressure resistance as well. So we have 2 places where you could get this information. One of these places is you can contact your the technical sales from your region, and you can ask them for a database with the mechanical performance of our most common products, and then you can input this database into the software that you use for your well design, and it can be very easy and very it can make the well design easier maybe for you. So you can do that. Our tech sales representatives are going to be happy to share this database with you. Then there is another place where you can get this information is on the VAM connection database site. So you go into this site, you put the LD, the wall thickness, the drift, the grade, and then you get all the details from the product. So those are the 2 places to go. And then just keep in mind that if you do not find it on the VAM connection database site, it does not mean that we cannot do it. It simply means that maybe it's a not so common product. Just contact us, and then we can confirm to you which is the collapse rating or the burst rating or whatever you need for that product.
So thank you, Beatrice, a lot. We would like also to thank you, all of you attending today's webcast. An on-demand version of this webcast will be available for you in the coming days and will be emailed to everyone soon. If you have any additional questions or requests, feel free to contact Maria Beatriz directly. Thank you and have a good day.